Hello and welcome to the second lecture on finite field for error control coding. My name is Sumit Kumar Chaube and today we are going to discuss about field. In the last lecture we discussed about group. So first we are going to review what a group is, because we are going to need that definition today as well, and then we are going to proceed on a general field. So a group is basically a doublet. It's a set together with an operation star. This doublet is going to be called a group if it is going to satisfy certain axioms, namely closure. So for all a b element of G, a star b should also be element of G. This is what we mean by closure, that result of the operation, binary operation star, should be in G only if the source are in G. Then there is associative law. The binary operation star is associative. What it means that for all ABC element of G, A star B star C is actually equal to A star B star C. So there is no problem when you change the order of your operation. Then there is identity. G contains an identity element E, and identity element G of G is going to be unique, and the property of identity element is that it is not going to change your element if you operate it with the star. So A star E is actually equal to A, and then E star A is also going to be equal to A. Then there must exist an inverse. What we mean by inverse, that for any element A in G, there exists another element A dash in G called inverse of A, such that A star A dash is equal to identity element. Now inverse must exist for each and every element, and inverse is going to be unique. In the similar manner, this identity is also going to be unique. In general, star represents two operations. We can have either this star equal to, either this star is going to be addition, or it can be multiplication, or sometimes we denote multiplication by simply dot. Okay, so this is the definition of a group, and this is something that we have already discussed in the last lecture. Now group does not need to be abelian, means it does not need to satisfy commutative operation, but if a group is satisfying this commutative operation, then it is called a abelian group or commutative group. Now we are going to proceed to the definition of field, and we will see what a field is. So as a group is doublet, a field is triplet. What I mean by triplet is that it is with a set F together with two operation. In general, it is going to be multiplication and addition. So this triplet, a underlying set F, addition and multiplication, will be called a group if it is going to satisfy certain condition. And the first of one of those condition is that this set under addition, this set together with the operation addition, is a commutative group, means that it is going to satisfy all the axioms of a group, as well as it is going to be commutative. Now the identity element with respect to addition is called additive identity and is denoted by 0. It is also called a 0 element. Second condition is that non-zero element of this set F is a commutative group with respect to multiplication. Okay, and the identity element with respect to multiplication is called multiplicative identity of F and is denoted by 1. So 1 is always going to be multiplicative identity of the group. It is also called unit element. Now the third condition, multiplication is distributive over addition. That is, for any three element A, B, C that are element of F, A times B plus C is actually equal to A times B plus A times C. So you can see that this multiplication operation is actually distributive over addition. Now vice versa is not true. What I mean by that A plus B times C is not equal to A plus B times A plus C. So multiplication is not distributive over addition is not distributive over multiplication, but multiplication is actually distributive over addition. So with these three conditions, you can have a field. Now some fact about the field, that the order of the field is the number of element in the field F. For example, if you have set F and the element of set are simply 0 and 1, there are only two elements here, then the order of this group will be F. This is written like this, and this will be equal to 2. So order of the group is going to be 2. Now A minus B is actually equivalent to A plus minus of B. As I told you in the last lecture, that subtraction is actually addition in disguise. So you can see that A minus B is actually equal to A plus minus of B, where minus of B is called additive inverse of B, and A divided by B is actually equivalent to A times B inverse, B to the power minus 1, and B inverse is actually called the multiplicative inverse of B. So for A, addition with respect to addition, additive inverse is minus B, and additive identity is actually equal to 0. With respect to multiplication, multiplicative inverse of B is B inverse, and multiplicative identity is 1. So to summarize, this is going to be a group. This set F, addition and multiplication, is a group if and only if multiplication is distributive over addition and all the elements of this field F is going to satisfy 5 of these axioms. So 4 of these axioms are already for the what you can say for group, and the next one is required for a field. So there must be closure, there must be associative law, there must be identity, and identity element with respect to addition is going to be 0. There must be an inverse with respect to addition is minus A. So minus A is going to be inverse of A, and it must be commutative, that A plus B is actually equal to B plus A. Now non-zero element of F is going to form a group with respect to multiplication, and it should be a commutative group. So there must be closure, there must be associative law. The identity element with respect to multiplication is going to be 1. Okay, and this 1 must exist. So in general, 0 and 1 must be part of this set F. So F should contain 0 and 1. Apart from that, they can contain some other element as well. So simplest group can be, one of the very simple group is simply 0, 1, and this is actually a binary group. We will discuss about that as well. Okay, now inverse is also going to exist for each and every element. So for with respect to addition, the inverse was minus A. With respect to multiplication, the inverse notation is A to the power minus 1, or we simply call it A inverse. Okay, and we should also have commutation with respect to multiplication. A times B should be equal to B times A. So this is the definition of a field. Now we are going to look at some examples of field. We will see whether a particular set together with these two operations is going to be a field or not. So the very first example that we are going to look at is integer with operation addition and multiplication. Now you can see that with respect to addition, if you have two elements A and B, then A plus B is also going to be a integer. If a and b is integer, then a plus b is also going to be an integer. Similarly, a times b is also going to be a integer. So there is no problem with respect to closure. Associative law is generally satisfied with respect to addition. Multiplication, there is no problem. Now identity element, we already have 0 here. So identity element with respect to addition is 0, and identity element with respect to multiplication is 1, and 0 is actually not the part of this multiplicative group, because this multiplicative group is non-zero element of this set F. Okay, now this is also going to have an inverse. So for example, if you have an integer 3, then 3 inverse, let me simply write it that inverse of, let me write, then 3 dash is going to be equal to minus 3. Now here inverse is 3 to the inverse is going to be 1 upon 3. Now 1 upon 3 is not an element of Z. So this is not going to satisfy inverse property. And we have with respect to addition we have inverse, but with respect to multiplication we don't have any inverse. So that's why this is not going to be a field with respect to addition and multiplication, because this axiom is not satisfied. Okay, so basically inverse doesn't exist for each and every element with respect to multiplication, or multiplicative inverse doesn't exist with respect to in this group, so that's in this field. So that's why this is not going to be a field. Now we are going to see another example. Now we have rational number with addition and multiplication. Here you can say that it's going to satisfy closure, it's going to satisfy closure. If you have two integers, if you add them, the third integer, the result is also going to be an integer, and if you multiply them, the result is also going to be the result is also going to be a rational number. Associative law is going to be satisfied with respect to addition, with respect to multiplication as well. Identity element with respect to addition is 0. Identity element with respect to multiplication is 1. Inverse here is for any a element of Q. The inverse is, let me simply write that a dash is going to be minus a, and here a inverse is going to be 1 upon a. And since there are only non-zero element here, so there is no division by 0 problem here. So 1 by a, if you have a rational number and you simply divide it by divide 1 by that rational number, the result is also going to be a rational number. So this is also going to satisfy. So inverse exists for both of these cases. Now it is also going to be commutative. There is no problem. A plus b is going to be equal to b plus a, and a times b is also going to be equal to b times a. So commutative is also there. Apart from that, distributive property is also going to be satisfied. One example here is that 3 times 2 plus 2 is actually going to be equal to 3 times 2 plus 3 times, let me write the 2 plus 4, then 3 times 4. So this is all therein. So all these axioms are actually satisfied. So this is going to be a field. So Q together with plus and multiplication, where Q is a set of rational number, is going to be a field. But integer with respect to addition and multiplication was not a field. Now we are going to see another example here. Now this is something called prime field. It is also a finite field. Why I'm saying this is now a modulo 5 addition and this is a modulo 5 multiplication. So we have modulo 5 addition here and modulo 5 multiplication here. And the group of the element are 0, 1, 2, 3 and 4. So to prove all these property, we have already discussed this Cayley table. Okay, we have discussed what Cayley table is, and I have given two Cayley table here. One is with respect to an addition, another is with respect to multiplication. So you can see here in this case that result of this modulo 5 addition, actually I have given this plus, but it is you think that this is going to be a modulo 5 addition. Modulo 5 addition is all these elements are from 0 to 5, and each and every element is different in each column and each row. Apart from that, each and every element contains 1. Since each and every element contains row contains 0. So for example, in the first row you have 0 here, in the second row you have 0 here, in the third row you have 0 here, in the fourth row you have 0 here, and the fifth row you have 0 here. What does it mean? It means that inverse exists for each and every element. So inverse is going to be satisfied. We already have identity element that is equal to 0. Closure is going to be satisfied because you don't have any other element here. Associative law is going to be satisfied. Inverse is going to be satisfied. And it is commutative. The reason why it is commutative is very simple. You see that this is actually symmetric around this main diagonal. So along principal diagonal it is symmetric. You have 1 here, then you have 1 here. You have 2 here, then you have 2 here. You have 3 here, then you have 3 here. You have 4 here, you have 4 here. You have 4 here, you have 4 here. You have 3 here, you have 3 here. You have 1 here, you have 1 here, and 2 and 2. So you can see that this is this is going to be symmetric with respect to diagonal element. What does this symmetry tells us? That A plus B is actually equal to B plus A. This is what this symmetry tells us. So it is going to be a commutative. So this is commutative. Now next we are going to discuss with respect to multiplication. Now with respect to multiplication, I have to only look at non-zero element. So this 0 element I am only going to cross them out. So you can see that 1 2 3 4, this is going to be our group. This should form a group and commutative group at that one. So you can see that identity here with respect to multiplication is always 1. So we have 1 in each and every row or every column. Okay, so in each and every column you have identity element. All these elements are different and all of them are from 1 2 3 4 only. So that's why you have closure as well, you have associativity, you also have inverse because 1 exists in each and every column and each and every row. So you have inverse there, and it's going to be commutative. That's very easy to see, as I told you, that if we take the diagonal element, here, if we see the diagonal element here, then you can see that with respect to diagonal element, all the elements are symmetric. So you have 2 here, then you have 2 here. So these 2 are there. Then you have 3 here and then 3 here. You have 4 here, then you have 4 here. Now you have 3 here, then you have 3 here. You have 2 here, then you have 2 here. So you can see that with respect to principal diagonal, this is going to be symmetric, and that's why it is going to be commutative as well. So this is commutative. And in addition to that, now the next thing is that we should have this modulo 5 multiplication should be distributive over addition, and that's very easy to show. So you can do that. Let's put that as homework. So your homework is that, so that here modulo 5 multiplication is actually distributive over modulo 5 addition. Okay, so this is going to be a group, and this group is called finite group. This is going to be a field, and this field is going to be called finite field. Why this is finite field? Because the number of element here in the underlying set F is finite. So you see that order of this field is equal to 5, And if you have a prime number here, this is also a prime number, 5 is also a prime number. Because of that reason, this is also called a prime field. And all the finite field you will see like this defined under modulo addition and modulo multiplication are in general going to be prime. Okay, so this must be prime. If this is modulo 4 multiplication and modulo 4 addition, then you cannot define a field, because we have already seen that with respect to addition that was a field, that was a group, but with respect to multiplication that was not a group. So it has to be a group, commutative group, a commutative field. So commutative group with respect to both addition and multiplication, and it is not going to be satisfied if this is not a prime number. Okay, so this is one of the example of field. Now next we are going to discuss certain properties of field. So the property number 1 here is that for every element a in F, 8 times 0 must be equal to 0. I had actually in the Cayley table I have already written that 0 times 0 is 0, 1 times 0 is 0, but we have to prove this, that this is actually true. Okay, so we already know that a times 1 is actually equal to a, right? So I can show that 8 times 1 plus 0 is going to be actually equal to a only, isn't it? Right? So a plus a times 0 is going to be a, right? So you can see that from here that a times 0 should be equal to 0. So if you take this right side, then you have a, and then in this side it is going to be minus a. So a times 0 must be equal to 0. So we have proved this first property. Now second property is that for any two non-zero element a and b element of F, a times b should not be equal to 0. If you have two elements and they are non-zero, it means non-zero element of this this field F forms a multiplicative group, right? Non-zero element of F must be a commutative field under multiplication. It means a times b should be non-zero element of F only if a and b are non-zero. So this directly follows from the definition. Now third thing is that a b element of F, if you have two element a b element of F, then if a times b is equal to 0 and a is not equal to 0, then b must be equal to 0, right? If a times b is equal to 0 and we are certain that a is not equal to 0, then b is going to be equal to 0. And it's also very easy to prove. You can take this as your homework and show that this is indeed true. Now property number 4, that a times b equal to a times c is equal, if a times b is equal to a times c, this is actually called cancellation property. Cancellation property. It means that if you have a times b equal to a times c, it implies that b is equal to c, and a should not be equal to 0. If a is equal to 0, then even if b and c is not equal, this is going to be true. Okay, so this is prerequisite. Now this is also very easy to prove. You pre-multiply by a inverse on both sides, and you can have a inverse times a times b, and then you have to pre-multiply on the right hand side as well, a inverse times a into c, and this is going to give you one multiplicative identity. So you will have b equal to c. Okay, so these are some of the properties of the field. So with discussion of this these four property, I'm going to conclude this lecture today. In the next lecture we are going to see finite field, field like this one, 0 1 2 3 and 4. under modulo 5 multiplication and modulo 5 addition, and we are going to see certain interesting properties of this group and in these field, and these are the kind of field that we are actually interested in, finite field. Okay, these are also called Galois field in the honor of Galois field, actually in the honor of Évariste Galois, and we will discuss about them in the next lecture. So thank you.